Hello, welcome to lecture 12 of the course. In the last lecture, we have started discussing some fundamental concepts associated with quantum computation. We will continue our discussion in this lecture. So, let's begin. In the last lecture, we learned about some basic elements of quantum computation. We learned that at the core of quantum computation is the so-called qubit. A qubit is simply a superposition of two states, K0 and K1. And in a typical physical settings, K0 may represent a vertically polarized light and K1 may represent a horizontally polarized light. So in this case, in the physical settings that I'm talking about, we are using photons as our qubit system. So if I consider a photonic qubit, then the quantum state would be of this type C0, that's the coefficient or the probability associated with finding the photon to be in the vertically polarized light. C0 mod square will give you that probability, and then C1 is the amplitude coefficient associated with the horizontally polarized photon. So this is one setting where we can have photons as our qubit, or we can also have a situation where K0 can be represented by spin half of the electron. For example, if we consider electron to be a qubit system, if we exploit electron for qubit, then spin half would be represent K0 and K1 would be represented by the spin down state of the electron. And in this case, the spin qubit, if I talk about, then the quantum state for the spin qubit is going to be the superposition of the up state, and associated amplitude would be say A0, and for the down state, that means spin minus half state or spin down state, it would be A1 is the amplitude coefficient associated with that. So this is going to be the representation of a spin qubit system. Now, as we have learned that the most useful representation of the qubit is the so-called Bloch sphere, and we learned that in the case of the Bloch sphere, every point on the surface of the Bloch sphere, so here I am drawing a Bloch sphere, every point on the surface of the Bloch sphere represents a qubit state. And as we have learned from our earlier classes, that this south pole represents K0 and this north pole may represent K1. And we also learned that when we talk about qubit operation or qubit manipulation, actually we can visualize it as a qubit going from one point on the Bloch sphere to another point of the Bloch sphere. For example, if I take K0 from this point S to another point, say M on the Bloch sphere, M is placed at the equatorial plane of the Bloch sphere, where this x-axis is cutting here at the equatorial plane at this point. And we know from the earlier lecture that this point M is basically the superposition of K0 and K1. So this particular point I can approach from the point S by various trajectories. I can take this path, or I can take this path. There are many ways I can reach from the point S to the point M, and these I can basically achieve by the so-called Hadamard gate operation, as we have learned in the last class. So if I operate by the Hadamard gate on the qubit state 0, then it is going to take me to the superposition, equal superposition of K0 and K1. And in the last class we have discussed about Hadamard gate, we have discussed about X gate, C0 gate, and so on. And finally, we also learned in the last class about quantum entanglement, because as I told that for effective quantum computation, these qubits has to be entangled with one another, and entanglement is a extremely important property in quantum computation. And we briefly discussed what is quantum entanglement. To tell you that once again, suppose we have a system A and system B. System A and B are separated from each other by long distance, and if this composite system has this quantum state, it's represented by the state vector psi AB, k psi AB. But if I cannot write it as a product state, that means
product or the direct product or the tensor product of their individual state. If I cannot do that, if I cannot write it as a product state, then I say the system A and system B are entangled with one another. As an example, say we have a composite system defined by the state vector, which is one of the Bell state as we have discussed in the last class. Say k psi minus is equal to 1 by root 2 k 01 minus k 10. This state represents an entangled state. In no way you can actually express it as a product state. In fact, this given state represents the so-called EPR state, or the also called Einstein. EPR is the short form for Einstein Podolsky, and Rosen. Einstein-Podolsky-Rosen pair. This particular quantum state represents an EPR pair, Einstein-Podolsky-Rosen pair. Let me explain it a little bit more clearly. Suppose we have a source and this source is emitting a pair of particles. One particle is going towards this direction and it is received by a person, say Bob, and the another particle is going in the opposite direction and it is received by a lady called Alice, and both Alice and Bob are separated from each other by far away distance. Now Alice measures her particle and obtains her reading as say K0, or she may measure it to be K1, and K0 here represents the particle spin state. Suppose the spin is found to be in the up state, and we know that that is going to be represented by say K0, or it may be she may actually measure the spin state of the particle to be in the down state, and then it is called K1. Okay, now depending on her reading, so depending on Alice reading or Alice measurement, Alice reading, the EPR state is going to collapse, or it is going to project it. It is going to project it to 0 1 or 1 0. What I mean is that, so because of the Alice measurement, this EPR state, which is a superposition which we have written as 0 1 K01 minus K10, this is going to be projected either to K01 or 10, and this is going to happen instantaneously. This process is going to take place instantaneously even when Alice and Bob are separated by a large distance. And what it basically means is that when it is getting collapsed to either this state or this state, this means that if Alice measures her spin state to be K0, particle state to be K0, this means that Bob is definitely, it basically implies, this implies that Bob is surely observe his particle state to be in K1, or if it is getting projected to 1 0, then Bob particle state would be in K0. This is what it means, and this is the essence of quantum entanglement. And the point to be emphasized here is that even though Alice and Bob are separated from very far away distance, once a measurement is made on Alice particle, it automatically forces the Bob particle to take a position. That means either it would be in the up state or it would be in the down state depending on the measurement of Alice, and this is the essence of quantum entanglement. Now let me discuss how to deal with quantum entanglement using the density matrix formalism. Let us say we have a entangled state, again represented by a state vector say k psi, and this is let me write it as alpha k0a 1b plus beta 0b 1a this way I am writing just to emphasize the fact that this particle 0, K0 here, it's a composite system I am talking about. 0 belongs to, in this here, in this term, 0 belongs to, K0 belongs to the system A, K1 belongs to system B, and in this term here K1 belongs to system A and K0 belongs to system B. And also you can immediately make it out that in no way I can write this K psi as a product state psi a tensor product psi B, okay, and that's why it is an entangled state. Now if I want to write the density operator corresponding to this state, so that's going to be rho is equal to K psi bra psi, and if I open it up, so let me just write K psi as alpha 0 1 plus beta 1 0. Just remember that this first Q1 state belongs to system A, the second one belongs to system B, and already we have discussed it so many times, so it must be clear to all of you. And this bra psi is going to be alpha star, because alpha and beta are complex quantities, their complex amplitude, it would be 1 0 plus beta star, actually this would be 0 1, okay, this would be 0 1, and this is going to be bra 1 0. And if I open it up, I am going to get mod alpha square K0 1 0 1 plus alpha beta star K0 1 bra 1 0, and I will have beta alpha star, you can easily make it out yourself, K 1 0 bra 0 1 plus mod beta square 1 0 K 1 0 bra 1 0. Alright, so this is what is going to be the density operator for this whole system. Now say we are interested only in system A, then you know that you just have to trace out the system B, and we have already discussed how to do this tracing operation while we have discussed about the reduced density matrix formalism. And if you do that, this is going to give you the density operator for the system A, and you are going to find it to be, say, mod alpha square. Please try to do it yourself. You will get it as 0 K0 bra 0 here plus mod beta square, you will get it as K1 bra 1. The point to be noted here that this belongs to the system A. Alright, so let me write here A, and this is a, in fact this is a mixed state, because if you see it carefully you can write it as a this density reduced density matrix for the system A. You can write it in this particular form, where Pi is the classical probability and this is your Ket I bra I, where I goes from I takes Ket 0 as well as Ket 1, right? So therefore you see this is the way we represent a mixed state. So when we have taken the find out the reduced density matrix, then we find that the system A is now in a mixed state, and it also refers to the fact that we have lost the complete information. We don't have the full information about the system A because it is now in a mixed state. And similar way you can find out the density operator for the system B. You just have to trace out system A from the density operator rho, and if you do that, again you are going to find it as mod alpha square. Here it would be K0, but this time it belongs to the system B. So this is what you are going to do. That I encourage all of you to please try it yourself, and you will find this. Okay, so again you see this is the density operator for the system B, and this is also in a mixed state, and that means you are losing the information about the full information about the system B. And this is happening because of the fact that system A and system B are entangled with one another, and when we have actually they are entangled, they are losing their individual identity, and we have to consider them in together. And also it actually tells this particular fact that if you perturb or disturb or measure one system, then automatically the other system is getting affected or getting disturbed. And this is what, as we have seen, is the so-called quantum entanglement. This offers us a tool to characterize entanglement based on the purity of the state of the individual system. If trace of rho b square is equal to 1, then it is clear that the state k psi is not an entangled state, because from our earlier discussion of density matrix, if trace rho square is equal to 1, that tells that the state is pure. And now here rho b is the density operator or reduced density matrix of the system B, and because trace of rho b square is equal to 1, it's a pure state, and that means that we have the complete information about the system B. Therefore, the system B cannot be entangled with system A. On the other hand, if trace of rho b square is less than 1, then system B is entangled with system A. Okay, now as you can see, this is a very nice way to quantify, or basically to check whether two systems are entangled or not. You just have to write down the density matrix of the system, then you have to find out the reduced density matrix of the system, say system A and system B. That means just you find the reduced density matrix corresponding to the subsystem A and B, and then if you find out the trace of rho square corresponding to A and B, then if you find, for example here, if you find that the trace of rho b square is less than 1, then you can confirm that system B is entangled with system A. And similarly, if you find that trace rho a square is less than 1, that means this implies A is entangled with the subsystem B. Okay, now let me discuss a few measures of quantum entanglement, and these measures gives us a quantification procedure to know how much two systems are entangled with one another. And it's a huge subject, and I'm not going to discuss all the measures. I'm just going to give you some ideas only. And one of the measure that I'm going to discuss is the so-called entropy of entanglement, or von Neumann entropy. And so this is what I'm going to discuss now. That's called the entropy of entanglement. Also, it is called von Neumann entropy. I will not be able to discuss it in great details, but I will just give you some basic idea. So first of all, this entropy concept, as you know, is coming from physics. In thermodynamics and statistical mechanics, all of you have studied about entropy, and in statistical mechanics, entropy, symbolized by this symbol S, is defined as kb logarithm of capital omega, where kb is the Boltzmann constant. This is the Boltzmann constant, and you know that capital omega is the so-called number of microstates of the system. It's called the number of microstates. It's also known as the thermodynamic probability. As an example, if we talk about, say, ice, water and vapor, right? In ice, you know that it has low entropy compared to water. So say entropy of ice, if I consider, then entropy of water, if we consider an entropy of vapor, because of the fact that the number of microstates in ice is less than that of water, and the number of microstate in vapor is greater than that of water, so it is clear that entropy of ice is less than entropy of water, and entropy of water is less than the entropy of vapor or steam. Okay, because the number of microstates in vapor it is greater than, it's greater than, number of microstate in vapor is greater than water, and number of microstates in water is greater than that of ice. So that's the reason you out of these three states, vapor has the highest entropy. Okay, so this fact is already known to you, and in fact this expression for entropy, S is equal to kb logarithm of omega, where the base is exponential, it's natural logarithm, it can be expressed in terms of probabilities as well, and it can be written as minus kb summation sum over I pi logarithm of pi, where this pi is the probability of obtaining, this is the probability of obtaining the ith microstate, obtaining the ith microstates. Okay, it's so if you are not following this part much, so don't bother about it. We will soon discuss entanglement in the context of this quantum state, and we will see how to actually utilize it to do some calculations. And if you learn that, that is also going to be good, but if you can follow it, I'm just going to make the connection how this idea is basically extended to the case of the entropy for quantum information theory. So this idea of entropy, thermodynamic entropy or statistical entropy is used by Claude Shannon in classical information theory. So Shannon has picked up this idea of thermodynamic entropy, and he used it in classical information theory. There entropy is defined like this: S is equal to sum over x p of x logarithm of p of x. Now here this guy p of x is the probability, this is the probability of outcome associated with the measurement of random variable x. Okay, in information theory, entropy is used to quantify the degree of correlation between systems, and the correlation is a measure of information. Now when two systems A and B are correlated, if A and B are correlated, so the question that is generally asked is how much information of A is contained in B or vice versa. This idea of Shannon is extended to quantum regime by von Neumann, and von Neumann was a famous mathematician and a physicist, in fact a great information theorist as well. So von Neumann entropy is defined as follows. So here S of rho, this entropy now is a function of density operator or the density matrix, because in quantum mechanics the state of a system is in general defined by the density operator or the density matrix, and von Neumann entropy is defined as S of rho is equal to minus of trace of rho logarithm of rho. Now in fact this formula can be worked out from the Shannon formula as well, but here with a difference. Now the Shannon formula, if I write it in the quantum domain, it is going to be of this form, but here this pi, because it is the quantum case, here pi is the probability of obtaining of probability of getting the system in the quantum state gets psi I. Okay, this is what pi is. Okay, that's the probability of getting the system in the quantum state gets psi I. Now it can be shown that von Neumann entropy formula can be written as S of rho. We can write it as minus sum over I lambda I logarithm of lambda I. Now here this lambda I are the eigenvalues of the density matrix rho. Okay, later on it will be more clear to you when I will do some examples. As we deal with qubits or two-state system, the logarithm base here is 2. So this is important to always keep in mind, that here the base of the logarithm is 2 because we are dealing with qubits or two-state system. Now before I proceed further, let me consider some example. Suppose we have a pure quantum state. Now if we have a pure quantum state, I can represent it by a state vector k psi. That means this is what I have, and the corresponding classical probability, as you know, is 1. So therefore, as per this formula for entropy, I have pi logarithm of pi with base 2. Now because we have just only one system, it's a pure state, so classical probability is 1. So instead of this summation, I have just only one term, and that is pi is equal to 1 here, and log of 1, so that is equal to 0. So what we see, that this is important result, that the entropy of a pure state is 0. This is quite obvious. That means that there is no disorder or nothing, randomness, anything. These things are not there because we have the full information about the quantum system. That is the reason it's a pure state. Now we saw from our earlier discussion that when two systems A and B are entangled, then the density operator corresponding to the system A and density operator corresponding to the system B corresponds to mixed state. Okay, they represent mixed states. This we discussed a while back. These are represent mixed state, both A and B, if they are entangled. Now if you find out the entropy, you are going to get that S of rho A is not going to be equal to 0. It would be non-zero. If it is pure state, then only it is going to be 0. So this gives us the idea or a measure of entanglement. Users have to calculate the entropy of entanglement for the system A and system B, and users have to calculate this quantity. For example, for the system A, S rho A is going to be minus trace of rho A log of rho A with base 2, and you are going to find out that this is not going to be equal to 0 provided system A is entangled with system B. And similarly for system B, you will have to calculate minus trace of rho B logarithm of 2 rho B. You are going to find that this is not equal to going to be 0. So we find that if von Neumann entropy of the subsystems are non-zero, then subsystems A and B are entangled. Let me now consider an example to clarify this concept. Let us say we have a composite system A and B, and it is represented by state of this composite system is represented by the state vector k psi AB is equal to, say, square root of 2 by 3 k 0 0 plus 1 by root 3 k 1 1. Now we have to find out whether this system A and B is entangled or not. Now here this 0 as usual refers to system A, and this belongs to system B. Similarly here, this first one is belonging to system A and this belong to system B. So we have to first find out the density operator or the density matrix for this composite system, and that is going to be, we just have to find out it the usual procedure, K psi AB, bra psi AB, and we have actually done this in an earlier class. Maybe in the previous class we have worked it out, so let me do it very quickly once again. So we have 2 root 2 by 3 square root of 2 by 3 0 0 plus 1 by root 3 1 1, and bra psi AB is 2/3 bra 0 0 plus 1 by root 3 1 1, and if I open it up, then I am going to get the density operator for the composite system as 2 by 3 0 0 0 0 plus root 2 by 3 k 0 0 bra 1 1 plus square root of 2 by 3 k 1 1 bra 0 0 plus 1 by 3 k 1 1 bra 1 1. Okay, now as we are asked to find out whether the system A and B are entangled and how much they are entangled, that we can find out by finding out the entropy of the system A and system B. Now to find out the density operator for the system A, we just have to trace out system B, and we have done so many problems associated with reduced density matrix, so you can immediately find out that if you trace out B, then you are going to get rho A is equal to 2 by 3 k 0 bra 0 plus 1 by 3 k 1 bra 1. Okay, now you can write it in the matrix form as follows. So you will have 2 by 3 0 0 1 by 3. Now as regards the entropy for this system A, so S rho A, the von Neumann entropy is going to be equal to minus trace of rho A logarithm of rho A with base 2, but more useful form of this von Neumann entropy would be this, where you write it as sum over I lambda I logarithm of lambda I, where lambdas are the eigenvalues. Now from this density matrix rho A, from here it is easy to see that the eigenvalues here are simply 2 by 3 and 1 by 3. So the von Neumann entropy corresponding to the system A is going to be simply minus lambda 1 is here 2 by 3 logarithm of 2 by 3 minus 1 by 3 logarithm base 2 1 by 3. So if you do the calculation, what you are going to get is simply 0.918, and as you can see this is non-zero, so therefore system A and system B are entangled. Now let us discuss about a very important topic called the no cloning theorem. It's a very important concept in quantum computation and it affects quantum computing quite deeply. The no cloning theorem is stated as follows. It is not possible to copy or clone an unknown or an arbitrary quantum state by using unitary transformation. And by the way, all of you know that unitary transformation is carried out by the so-called quantum gate operation. Let us prove this no cloning theorem. To prove that, let us assume that there exists, suppose there exists a unitary transformation capital U, which can copy or clone a quantum state. By cloning or copying a quantum state, we mean that this state, say k psi, can be copied to this blank state ket 0, and then because of this unitary operation, if it exists, then this state ket psi can be copied to the blank state or 0, and then we are going to have this. Okay, so let's say this is my equation 1. If such a unitary transformation exists, then what we can have, let me write it again. We can write this state ket psi into the blank state, and we'll have psi direct product psi. Or suppose we have another state, say ket phi. If this unitary transformation exists, then we can copy that also. We can write that into the blank state. So this is possible. If this is possible, then we can also copy this superposition state of ket psi and ket phi as well. So if you have applied this unitary operation on it, then we can also write it into the blank state, and then we are going to get it as we'll have here a ket psi plus b ket phi, and here this empty state would be now would be filled up with a ket psi plus b ket phi. If I open it, this whole direct product, then I am going to get the state a square ket psi direct product ket psi plus ab ket psi direct product ket phi. As you can see, then I have ba or ab ket phi direct product ket psi, and finally I will have b square ket phi direct product ket phi. So let me say this is my equation number 2. Okay, so this is very important, as we will see. So if my unitary transformation u exists, we can have such a unitary operator, then this is what we are going to get. Again, because u is a linear operator, so because of the linearity, I can also have u a psi plus b ket phi direct product with this empty state. I can have a u ket psi direct product ket phi plus b u ket phi direct product ket 0, and this is going to give me I am going to get a ket psi direct product ket psi, because now this is going to be written written here. Actually this should be 0. Okay, this is ket 0, this would be written here, and then I have b I have ket phi direct product ket phi. So let me say this is my equation number 2. Now you see, if I compare this equation number 2, no, actually this is equation number 3. If I compare this equation number 2 and 3, this is what we have. It is the same thing, and the result is, in this case the result is this equation 2. You can just see the right hand side, and here you can see the result is this on the right hand side, equation number 3. Just look at this expression. So let me, this expression here and this expression here on the right hand side of equation 2 and 3, if these two equations can be satisfied simultaneously or not, you can immediately see that this is not possible. Equation 2 and equation 3 cannot be satisfied simultaneously, because of that u cannot exist. So therefore, because equation 2 and 3 cannot be satisfied simultaneously, of course it can be satisfied simultaneously provided a is equal to 0 and b is equal to 0, but that would be absurd because you will not have any superposition state then. So now that is not possible. We cannot have a is equal to 0 and b is equal to 0. That's the reason these two equations cannot be satisfied simultaneously. You cannot have an unitary operator or unitary operation like this does not exist, and that means that we cannot copy or clone an arbitrary or an unknown quantum state by unitary operation. So this is basically the no cloning theorem, and this is extremely important. And in fact, one have to be careful when applying no cloning theorem. It is generally misunderstood a lot. For example, if the states that is going to be cloned is limited to say K0 and K1, we can definitely clone it. Okay, we can copy it because we know K0 and K1, they are no longer arbitrary, and this is the reason why we have this kind of an operation. Say if you operate on 1 0, okay, then you can get say 1 1, and if you recall that this operation is obtained via the so-called, what kind of gate? It is called the C0 gate. By C0 gate operation we have this, and here no cloning theorem, by the way, is not applicable because we know K0 and K1, they are no longer arbitrary. As a final topic, let me rush you through the so-called quantum teleportation. Now, quantum teleportation is a protocol to transmit an unknown quantum state of a qubit using two classical bits such that the receiver reproduces exactly the same state as the original qubit state. You can see that the unknown state is not transported or cloned, rather it is reproduced at the receiver's end. Let us discuss it. Say Alice needs to send the quantum state K psi, it's a superposition state K0 and K1. She needs to send this quantum state to Bob, and because she cannot copy it or clone it, she has to follow a certain protocol, and that's what we are going to discuss now. And both Alice and Bob share the entangled state, a Bell state. Say this Bell state is say phi plus, given as a 1 by root 2 K00 plus K211. So this is the state shared by both Alice and Bob. Here the first qubit belongs to Alice, the second qubit belongs to Bob. Here also the first qubit belongs to Alice and the second qubit belongs to Bob. Initially, Alice contains two qubits in her lab. One is this qubit K psi and the other one is from this shared entangled state. So both and Alice starts with this state. Okay, so as you can see here, this is direct product of this state, unknown state, which is to be sent K psi, and this is the entangled Bell state. And here these first two qubits 0 belong to Alice, and this third qubit, this belongs to Bob. Similarly here these two qubits belong to Alice initially, and this belongs to Bob. When I say initially, that means before anything is done. Okay, you will soon understand what I mean by this. And here this first two qubits belongs to Alice and this third one belong to Bob. And similarly here this first two qubits belongs to Alice and the third one belongs to Bob. Okay, now in Alice's lab, she is going to do certain operations as per this quantum teleportation protocol. First, Alice is going to apply the C0 gate operation in her two qubits. Okay, because now Alice is having two qubits, and while Bob's qubit is going to get unaffected. That's why this is given by this identity operation. That means Bob qubit is not going to be touched at all. So if the C0 gate operation is made on the Alice qubit, and you are already aware of what a C0 gate does, now here as you can see the first qubit, if I talk about the Alice qubit, the first one refers to the control and this second qubit refers to the target. Similarly here this is your control and this is your target. The first one is control and the second qubit is the target. Here the first one is control and the second one is target. And you know, as per the C0 gate operation, the target bit gets flipped if the control gate is 1, right? So because of this C0 operation, as you can see, you are going to get this particular state, and this is easy to see. This is going to remain unaffected, this is going to remain unaffected, but here this second qubit is now getting flipped, right, in this term, as you can see from here, because the control is 1. Similarly, if you look at the last term, because the control qubit is 1, the second qubit is going to flip to 0 here. So this is the state after C0 gate operation is done. Now Alice is going to make a Hadamard gate operation on her first qubit. Now if the Hadamard gate operation is done on the first qubit, then the second and the third qubit is not going to be touched. Now Hadamard gate operation, as you recall, Hadamard gate, if it operates on gate 0, then it becomes 1 by root 2 gate 0 plus gate 1, and if Hadamard gate operation is done on gate 1, then it becomes 1 by root 2 gate 0 minus gate 1. So this is what is reflected here. So this is what is done. First qubit is going to, and because of this root 2 factor, and root 2 factor is already there, so this become 1/2. So this is the resultant state after this second operation is done, which you can actually open it up and then you can write this particular term. And this one also you can rewrite it in this particular form. Now if you rewrite it in this way, so here I have rewritten after making the both the operations, C0 gate operations followed by the Hadamard gate operation, then this is the resultant state that Alice is having. Now as you can see, in Alice 2 qubit, now your Alice is having 0 0, then or she may have 0 1, or she may have 1 0, or she may have 1 1. So her qubits are 2 qubits are getting converted to either 0 0, 0 1, 1 0, 1 1 with equal probability. And as a result of the operation of Alice operations of C0 and Hadamard gate, Bob's qubit is also getting affected, and this is getting turned into the Bob's qubit is going to be a superposition of gate 1 and gate 0. Now Alice sent her measurement result to Bob through a classical channel, and this classical channel may be a telephone, and based on the information received from Alice, Bob in his lab is going to make some measurements or operation to reconstruct the original state. It is as follows. So in Bob's lab, depending on the information received from Alice, because Bob has no idea what his qubit is, by the way, okay, he is going to make just some kind of an measurement based on the information received from Alice. Suppose Bob receives the information through this classical channel that she got 0 0 as a result of her measurement on her qubits. Then Bob is going to do nothing on her qubit, so that's why this is identity. So this is the state Bob is going to have after this operation. That means he is going to get the state a superposition of 0 and 1, a0 plus b1. In fact, this is the state which originally Alice intended to send. Now you see, so Bob is able to have the intended state. Now if the information received from Alice is 0 1, then Bob's state is a gate 1 plus b0, which is not the intended state. So Bob is going to make a X gate operation or NOT gate operation, and that's going to flip gate 1 to 0 and gate 0 to 1, and then he will be able to have this particular qubit state, which is the intended state that was originally needed to be sent. And on the other hand, if Alice information that Alice sent is that she is getting 1 0, then Bob is going to make a Z operation. By the way, this Z operation is basically this sigma Z Pauli matrix. If you recall, sigma Z is the operation referring to 1 0 0 minus 1. So this is sigma gate Z operation or Z gate operation. X, if you remember, this basically the so-called sigma X operation, the Pauli X matrix. It is 1 0 0. No, actually it was it was you have 0 1 1 0, right? This is sigma x 1 0. This is going to be made, and if z operation is done, then Bob is going to get this as his qubit, and this is again the original state which was intended to be sent by Alice. And finally, if Alice says that she got 1 1, then Bob is going to make a y operation, and this y operation is akin to the sigma y operation, sigma y Pauli matrices. Only the thing is that you now, rather than minus I, you can have -1 here and 1 here. Okay, even if you have minus I, it doesn't matter. So actually it would be multiplied by a factor of I, and then it can be absorbed in A and B, and you are going to recover the original quantum state which was intended to be sent. So this is in short the so-called quantum teleportation protocol is, and I can represent it very quickly through a schematic. So what we have is that originally the Alice was having this unknown state ket psi which she wanted to send, and both Alice and Bob share an entangled state, Bell state, and this Bell state can be constructed by this process. So if you send this particular if the input is to the Hadamard gate is 0, and in the second one if a NOT operation is made, then this is going to result in, as you can check, I think we have done it in the last class. So this is going to generate the entangled state phi plus, and this entangled state is now shared by both Alice and Bob. So these first two wires here, the first two channel belongs to Alice, right? So Alice is going to have this state ket psi and the first qubit here. So this is what Alice is having. So this is the first two qubit belongs to Alice initially, and the third one belongs to Bob, right? Now what Alice is going to do, now Alice first is going to make a C0 operation. So this first one is the control, and then you have this target here, and after this C0 operation, Alice is going to make a Hadamard gate operation on her first qubit, and then she is going to make a measurement. If the measurement is done, so she is going to do measurement on her these two qubits. This is the measurement she is going to do, and this measurement result she is going to send to Bob through a classical channel. So this is our classical channel, and this result is conveyed to Bob through this classical channel. And what Bob is going to do, Bob is going to make a unitary measurement as per the protocol, as directed in the protocol. Bob is going to make a unitary measurement on his qubit, and this is going to result in Bob's laboratory. The original state ket psi is going to be what Bob is going to reconstruct or get. Okay, so this is in short the so-called quantum teleportation protocol is.
Let me stop here for today. In the last few lectures, including this one, we have covered quite a few concepts. Based on these new lessons that we have learned, we are going to solve some problems in the next problem solving session. See you then. Thank you so much.